Say a student comes into my office hours and says they kind of understand linear independence, but they don't know how to actually check through it. Let's work through it. All right, so the formal definition here is that we have a set of vectors v1 through vk and weights c1 through ck, where k is some sort of real integer. And we're saying that if we set them all the way and we add them all together, they're equal to the zero vector. Now, the key difference is between independent and dependent, the weights are different. So the weights for independent will be all zero. And this means it's the trivial solution. And for dependent, this will be the non-trivial solution because the weights will not all be zero. At least one of them will be a real number. So let's work through an example to see how this looks. Say we have these three vectors, and we're going to put them into an augmented matrix equal to zero at the end. So 1, 0, 1, 0, 1, 1, and 1, 1, 2. And we'll reduce it down to get to reduced row echelon form, which we'll then be able to use to see if there's either all the weights need to be zero, or at least one of them is non-zero, which means it's non-trivial, which means it's linearly dependent. Okay, so first step is let's do row 3 and have it minus by row 1. And this will get us to a 0 in that corner, which is awesome. And then these other values will stay the same as we didn't do anything to affect those rows. Now we can see pretty clearly that row 2 and row 3 are equal. So if we were to minus now row 3 by row 2, we will get all zeros on the bottom. And then again, row 2 and row 1 stay the same as we didn't do any operations with them. So the first important thing to note here is that we have a pivot in row 1, column 1, and column 2, but there's no pivot in column 3, row 3 at all. So this tells us that C3, one of our weights, is going to be a free variable. So it can be anything we want. So immediately we know this is linearly dependent because we can set C3 to be anything, and that means there's infinitely many solutions and there's a non-trivial solution because C3 can be anything, including not zero. Now, C1 and C2 we can find by setting up equations given from this. C2 plus C3 is equal to 0. And this means that C1 is equal to negative C3 and C2 is equal to negative C3 as well. Now, if we were to say C3, for example, equals 1, we'd get that C1 is equal to negative 1 and C2 is equal to negative 1. And this is, again, just one of infinitely many solutions that can exist because C3 can be, anything in the infinite range of numbers. And if we use these weights and go back to our equations up here, which is the same for both, and we plug it in, we get minus vector 1 minus vector 2 plus vector 3 is equal to that 0 vector. And if we were to rearrange that, we'd get that v1 plus v2 is equal to v3. And if we look up at our original vectors, we can see that's true if we did the algebra there. So one quick trick that can help you solve these more quickly is that if you have a set of vectors v1 through vp in some sort of space R of n, if p is greater than n, meaning there's more vectors than the size of your space, then it's always going to be linearly dependent. And now if we look at an example here, we have three vectors and we have a space of 2. We row reduce our augmented matrix here, and we see that we have a free variable C3. And that's why this always works, is because if you have more vectors in your space than the size of the space, then you're always going to end up with some sort of free variables. And these free variables tell us it's linearly dependence. So to sum everything up, if you're given a set of vectors and you want to know if they're independent or dependent, you want to set up this augmented matrix, which is going to tell you what are your weights. Are they all zero? Are they at least non-trivial? So one of them's not zero. And you can basically tell that just by looking as, row reduce it, see if there's a free variable or not, and that'll tell you about linear independence. Thank you.